Okay, so today we're going to be talking about the chain rule and higher order derivatives. So higher order derivatives we're going to be learning about derivatives with shortcut rules when we're taking the derivative of a function as opposed to just a single variable. So the benefit of learning shortcuts when it comes to taking derivatives is because the process of taking derivatives from like a function or from a graph, as it says here, is not always practical and can be time consuming. So we learn shortcuts to calculate a derivative more quickly. So we also use these shortcuts because we can learn about more diverse types of problems and where we can use them. And this particular lesson about higher order derivatives is important for numerous types of problems. So the chain rule explains the way of taking a derivative when you have more than one variable, like in a function that you need to differentiate. So for example, in a function such as this, it can be rewritten as x squared plus 1 to the 1/2. So before we learn about the chain rule, we would only know how to take the derivative of a function like this. We would only know how to take the derivative of this single variable here. But with the chain rule, we can take the derivative of this group here of a function. So before we learn about the chain rule, it's important to understand the breakdown of a function like this, like a composite function here, and the different parts that we'd be differentiating. So for this table, it's important to learn that if you substitute in u for g of x, substitute in u for a function, and you're taking the derivative of f of g of x, or f of u, then you know that the derivative of that is the derivative of f of g of x is equal to f prime of g of x times g prime of x. So to look at this in a more literal way, if we consider u to be g of x here for these different function values, then we can look at it and we can decompose this composite function. So if we plug in u for g of x, and we know that f of g of x is 1 over x plus 1, then we can substitute in u for x plus 1. And if u is x plus 1, and f of g of x, or f of u, is 1 over x plus 1, then we know that f of u is 1 over u. So same thing here. So if we know that u is 2 of x, or this is a composite function, if we consider sine to be the f and 2 of x to be the g of x, then we know that f of u is sine u. Same thing here. If u is, if we consider u to be like the inside part of a function, like if we look back up here, this 6x, or this x squared plus 1, or this, then we know that u would be 3x squared minus x plus 1. And if we know that it's f of g of x, then we know f of u is u to the 1/2, or root u. Finally, another trigonometric function. So if we know that u is the inside of the function, so u is tan x, and f of u is u squared. So that's our first example, is breaking down a composite function. So next, we're going to be looking at using this chain rule for an equation like this. So the general formula for the chain rule is if y equals u of x to the n, where u is a differentiable function of x and n is a rational number, then the derivative of u of x to the n is n times u of x to the n minus 1. So basically you would be bringing down this n here, just like here, and then subtracting 1. So knowing this general rule for the chain rule, this general formula, we're going to be using that to find dy dx for these composite functions. So if you look at this composite function and we use example 1, we know to break it down first into, say, g of x and f of g of x. So if we're breaking down this composite function, we know that this part in here would be u, or g of x, and this to the third right here, would be the f of g of x, or f of u. So if we're taking the derivative and we're looking back at this general rule, 3 would be n in this case, so we would bring the 3 down, so dy dx would equal, bring the 3 down, 3 times u to the x, which in this case is the inside, times n minus 1, which is 3 minus 1, or 2, times du dx, or in this case, like u prime. So then we would multiply by u prime. Remember, this is u. So we know the derivative of this will be 3 minus, again, chain rule, so we'll bring that down, 4x. Or to simplify, 9 minus 12x times 3x minus 2x squared, quantity squared. Remember to always bring down your derivatives. So, next, moving on, we have another composite function. Everything in the chain rule is composite function. So first we're going to look and we're going to find our, remember we're going to remember this, f of g of x, or f of u if g of x equals u. We're first going to find our u, our inside of the composite function. I say inside. So first and foremost, so this, typically it's going to be whatever is in the parentheses, or whatever is being, in this case, cubed, or to the 2/3, or to the negative 1/2. So first we're going to find our u, which in this case would be here, and then we're going to find our f of u, which in this case would be the 2/3. So dy, so we can rewrite this to make it simpler to look at, is x squared minus 1 to the 2/3. So dy dx, in this case, we know to bring down our exponent to the front, multiply by the function, x squared minus 1, and then to the n minus 1, which 2/3 minus 3/3 to the negative 1/3, and then don't forget to multiply by the derivative of u. That's what makes a chain rule, times 2x. So to simplify this, we would have 4x over 3 times the quantity of x squared to the 1/3. Okay, our final example. So first we have to find the inside of our function. So in this case, the inside would be this 2x minus 3. So we can rewrite this as -7. It's always easiest to rewrite functions so that it's something like this. Times 2x minus 3 to the -2. So the first thing we're going to do, bring down the exponent. In this case 14, because we're going to multiply it, bring it to the front, but this is in the front also, so we multiply those together. 14 times 2x minus 3 to -2 minus 1, which becomes the -3, times the derivative of u. Remember, this is u. So times 2. So we simplify, and dy dx equals 28 times the quantity of 2x minus 3 to the -3. Simplify further, 28 over 2x minus 3, quantity to the third. It's important to always bring down your dy dx. So the next type of chain rule that we're going to look at is a different type of composite function, and that is the trigonometric functions. So trigonometric functions are chain rules in that we have to consider this function to be composite. So if we think about it, we can rewrite this. So I'm going to bring this over here. If f of x, f of g of x is equal to sine of x, we're going to think back to this breakdown on our front page. We can think of this x as our g of x. And we can think of sine as our f of u. So to rewrite it more plainly, if g of x equals u, which equals x, then f of u, f of g of x, or f of u, is equal to sine of u. So basically, so these are formulas that you would have to memorize. So the derivative of sine of x is cosine of x. Derivative of tangent of x is secant squared x. The derivative of secant x is secant x tan x. The derivative of cosine of x is negative sine x. The derivative of cotangent x is negative cosecant squared x. And the derivative of cosecant x is negative cosecant cotangent. So an easy way to kind of memorize these is to remember them, is if you memorize these three over here. Derivative of sine of x is cosine x, derivative of tangent x is secant squared, derivative of secant x is secant x tan x. Then you can remember that their like kind of inverse sort of is either their 1 over value or negative. So in this case, these are like kind of reversible except there's a negative. These are reversible except there's a negative, and these are reversible except there's a negative. So in this example, example 4, we're going to prove that derivative of tangent x is equal to secant x. So to do so, we know that tangent of x, so we're just going to prove that this is true. We know that tangent x is equal to 1 over cotangent x. So we're going to use this. And so first thing we're going to do is we're going to rewrite it. So we also know that tangent of x is sine over cosine x, right? So the first thing we're going to do is we're going to use the quotient rule, which we've already learned. So if we take this and we do the quotient rule, and we do dx sine x over cosine x, we know that when you take a quotient rule, it's derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. So we know that this equals, I'm going to bring this down here for more room, cosine x times cosine x minus sine x times negative sine x. Because we take the derivative of sine, which is cosine, as we know here, times cosine minus sine times the derivative of cosine, which is negative sine x, over the denominator squared, which is cosine squared x. So next thing we're going to simplify. So we therefore know that cosine squared x plus, we're going to simplify the top, sine squared x all over cosine squared x. So we know from our Pythagorean identities that cosine squared x plus sine squared x is equal to 1. So we can simplify this further into 1 over cosine squared x. And 1 over cosine squared x secant squared x. Therefore, the derivative of tangent of x is equal to secant squared x. So this is just kind of just an easy thing, a nice just reminder that all of these work and that you can work through them if you'd rather not memorize them. Okay, so the next thing we're going to do is we're going to use the chain rule in the context of bigger problems and other formulas that we've already learned. So in this case, y prime, we know that when we're adding, we just take the derivative of each of the individual variables. So the derivative of x minus tangent x would be 1 minus, you can remember this, we remember it from here, 1 minus secant squared x. The next one. So in this case, we're going to be using a product rule because we have two separate variables here, two separate functions. So we know y prime is equal to, we remember from the product rule, remember we're going to go the derivative of the first times the second plus the first times the derivative of the second. So we know 1, the derivative of this is 1 times secant x plus x times the derivative of secant x, which is secant x tan x. So if we simplify this, so that's one way to remember your chain rule in context of like a more complicated problem. So in this case, you'd have to use chain rule and product rule. Okay, so this is where things are going to get a little more complicated. So in this case, we have quotient rule and two chain rules. So first, just separate these. So y prime is equal to, so first we're going to simplify it into, we know that this is, we can simplify this into cosecant x minus cotangent x. If we were to split this into separate parts, 1 over sine x minus cosine x over sine x, which 1 over sine is cosecant and cosine over sine is cotangent. So it's just a way to simplify it. So instead of using two chain rules and a quotient rule, so we only have two chain rules. So then we know y prime of cosecant of x is negative cosecant cotangent minus the derivative of cotangent of x, which is a negative, so plus cosecant squared x. Okay, so moving on. So this is just kind of like a rule of thumb for the things that we just did. So just easier ways to remember. So this is so what we just did was a bunch of simpler problems where we're using these derivatives of the trigonometric functions, but we're using them when u is not just x, when the derivative of u isn't just 1. So when the derivative of u isn't just 1, you use the chain rule, similarly to here, where you have to multiply by the derivative of u, or the derivative of g of x. Same thing here. So the derivative of sine u is cosine u, just like we just learned. But when u is not just a single variable x, when u is a function, say 2 of x or 2x or 6x or whatever it may be, you have to multiply by the derivative of that u. So the easiest way to learn that is just to apply it here. So if we think of this 2x as u and f of u equals sine u, then we can rewrite this as y prime is equal to cosine of 2x. We're going to take, first we take the derivative of this, times the derivative of u, times 2. We can rewrite this as y prime is equal to 2 cosine 2x. Simple enough. So same thing here. So if we consider this to be u, you can look back to these if you need to. And f of u is equal cosine u. And we can rewrite it as y prime is equal to negative sine of u times the derivative of u, which is 3. Simplify, y prime is equal to negative 3 sine 3x minus 1. Okay, same thing again. This is u, and this is f of u. Y prime is equal to, we can refer to these, secant 4x tangent 4x times 4. To simplify, 4 secant 4x tan 4x. Okay, so here, these are examples of derivatives of trigonometric functions when you only use the chain rule once. For example, taking the derivative of u prime, or taking the derivative of u here and multiplying by it. In these, you'll have to do the chain rule more than once. Right here, repeated use of the chain rule. So in order to find these derivatives, we're just going to go about the functions the same way we did before. So we consider this u, we can consider this f of u for now. So first thing is we know we have to bring down we can rewrite it. Well, it's always easier to rewrite as sine of 3x to the 4th. So we know that when we have a function as opposed to just a variable taken to an exponent, we know we have to bring the exponent down. So y prime is equal to 4 sine 3x to the 3rd. Then we know we have to take the derivative of the inside. So the derivative of sine of 3x would be the same thing that we just did here. Cosine 3x times 3. Here we just did the chain rule here by bringing down 4 times n minus 1, right, times the derivative of the inside. And then we did it again, because the derivative of the inside isn't just cosine x, it's cosine 3x times 3. So then we can simplify. Y prime is 12 cosine 3x sine cubed 3x. Don't forget that cubed right here. And there you have it. So again, we can rewrite this as secant of x over 2 to the 1/2. So first we're going to bring down the exponent. 1/2 of secant x over 2 to the negative 1/2, always n minus 1. And then we have to multiply by the derivative of the inside, which in this case is secant x over 2 times tan x over 2 times the derivative of u, which is going to be 1/2. So to simplify, 1/4 secant negative 1/2 of x over 2 times secant x over 2 tan x over 2. So we can simplify this again because this is to the negative 1/2 and this is to the positive 1. So this turns into secant to the positive 1/2 of x over 2 times tangent x over 2. So I'm going to bring this last example, I'm going to bring this down here just so I have more room. So if y equals cotangent of 3x over 2, quantity to the 2/3, first thing, bring down the exponent, 2/3, cotangent 3x over 2, quantity to the negative 1/3, times the derivative of the inside, which isn't just cosecant squared x, it's cosecant squared of 3x over 2 times, because the chain rule, times 3 over 2, which is the derivative of this right here. Then we can simplify. Y prime is equal to, remember this is negative, sorry I forgot my negative. Y prime is equal to negative cosecant squared of 3x over 2 over cotangent 1/3 3x over 2. Okay, so that's our last example. Now you know how to do the chain rule.